Hello everyone. First of all, I would like to introduce myself. My name is Vivek Aryan, and currently I am pursuing MTech in Applied Geology from Graphic Era Hill University, Dehradun, and I have completed my BTech in Geoscience Engineering from University of Petroleum and Energy Studies, Dehradun, in Department of Petroleum Engineering and Earth Sciences. So this video basically deals with the remote sensing technique for mineral exploration and land cover classification. Before wasting any time, I would like to show you the uh, the paper progress research work. Basically, I and one of my friend Vivek Kumar Mishra, we both are working on GSI project work. GSI State Unit Bihar, Patna. The project basically deals with the mineral exploration and land cover classification, and later on we will try to perform some geochemical characterization in our study area. So we are using the remote sensing technique. We are basically using the remote sensing technique for delineating the target exploration zones for mineral deposits and land coverage. So we are basically using the data Landsat-8 data, which has 11 bands, and and we are using software which is ArcGIS 10.4.1, and you can see this ArcMap interface. So it has different layers in table of contents, and I have already added all the layers that I have downloaded from Landsat-8 data package. So for your reference, I would like to show you band, let's say band 8 data. So actually these data are downloaded from a USGS website, from the Earth Explorer. So these you can see so this was the complete data package that was downloaded for Landsat 8 data. So it has 11 bands, and out of 11 bands, from band 1 to 9 are OLI, and from band 10 and 11, these are TIRS, you can say thermal infrared sensor. These are recorded from thermal infrared sensors. So let's say I am interested in band 8. So this is band 8 image. You can see these all are in TIFF format actually. So I would like to zoom to layer. So this is the image of a panchromatic Landsat 8 band, which has around 15 meter of resolution. So actually this data, we need only a small portion of this data, and because the area of interest that we are dealing is of a topo sheet which has topo sheet number 72L/6. So let me open my credential, use my credential to log in Survey of India Naksha. So you can see this after opening this SOI website. So we can search by sheet number, and as per the instruction from our mentor, Mr. Ashmir Mohammed sir. So the topo sheet number of the area 72L by 6 was our area of interest, and this is the metadata of the topo sheet, and I have already downloaded this topo sheet. This is the topo sheet, you can see, and this is our area of interest 72L by 6. So the data that we generally download from USGS Earth Explorer uh, has uh, has has area of has different area already covered in the Landsat-8 data. So we basically try to clip clip those bands, clip clip those bands. So so these four coordinates were noted down in MS Excel sheet. Their latitude and longitude are noted, and these and these latitude and longitude are saved in MS Excel .csv format, comma separated value format, and we can use this Excel sheet or .csv format to 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 locate this point in Google Maps by simply adding the layer, by uh, by by simply importing the CSV format, and we have located all these four coordinates. So we have saved this in a KML file, KML layer, and we have created a shape file. I will show you the shape file. We have created the shape file, this, and this is basically hollow shape file, and this is the area of interest 72L by 6 based on our topo sheet. So this is required area. So before wasting any time right now, so I would like to show you my methodology. I hope you all are familiar with Landsat-8 dataset, and the bands that are already present in Landsat-8, OLI and TIRS, the operational land imager and thermal infrared sensors. So all 8 bands have their own application in alteration mapping. So band 6 and band 7 are basically short wave infrared, and band 10 and 11 are thermal infrared sensors, and the basic sensors like band 2, band 3 and band 4 are blue, green and red, you can say the RGB, and band 5 is near infrared, and they all have their own applications based on their wavelength and the amount of reflectance. So band 10 and band 11 have poor resolution, you can say, but they have high wavelength, whereas band 8 has a great resolution with 15 meter of resolution and with lower wavelength, you can say. Significantly lower wavelength was present there. So this was the proposed methodology of our progress work that we achieved till now. So first of all, we downloaded the Landsat-8 data package, which was around 1.1 GB, and after that we performed atmospheric correction. So this was basically converting the digital number values because we are dealing with a raster image, so we are converting the digital number values to a top of atmosphere reflectance, and these reflectance values we can convert from. Already these values are present in metadata, and with the help of metadata we can actually convert our DN values to TOA reflectance, and after this we try to correct the sun angle or sun elevation, and some of the factors like elevation was already present in the metadata that we downloaded from Landsat-8 data, and I would like to show you the metadata. mm, let's let's have a look to our metadata. So this is the Landsat-8 metadata file. Sorry. So we are basically interested with reflectance reflectance mult band 1 to band 9, and reflectance add band 1 to band 9, and you can see that this is around reflectance multiplied band 1 is around 2 into 10 to the power minus 5, around 2 into 10 to the power minus 5 from band 1 to band 9, and reflectance add bands are basically negative. These are minus 0.1. So there is a formula, or you can say there is an equation that we use to correct the atmospheric correction, or you can say we use to convert the DN values to top of atmosphere reflectance. And after the atmospheric correction, we basically tried to generate the spectral band indices, and after that we spectral band indices like NDVI, NDMI means using the vegetation indices, or water indices, or landscape indices, or built up indices, and also the geological indices also were involved in our in this work. So clay mineral, ferrous mineral, silicate minerals, and most important, we are interested in lithium bearing pegmatites or lithium bearing minerals like spodumene and lepidolite. Spodumene is basically a source of lithium, which is inosilicate lithium aluminium inosilicate, LiAlSiO3 whole twice, and lepidolite is mica bearing mineral, which is most abundant lithium bearing mineral, and is a good source of lithium actually. So this was the proposed workflow that we have achieved till now, and this was one of the paper uh, from Fernandez ETL 2019. So they have used the remote sensing technique for detection of lithium, and they have created a paper with this methodology. Like they have downloaded the Landsat, because they have used Landsat 5, Landsat 8, Sanital 2, and Aster data also, and they have used the principal component analysis, and then they have converted the digital number to radians, or they have performed the atmospheric correction, and based on this they have generated the RGB composite images and band ratio technique for identifying the lithium. Like for lithium bearing pegmatites, they have used the band ratio 3/5, and for lepidolite they have used the band ratio around 4/7, and these are all for Landsat 8 dataset. And for spodumene they have used Aster data for with the bands 1 upon band 3, So, uh, so generating the spectral band indices is is of utmost priority. So, normalized difference vegetation index (NDVI) is used to is used for displaying the greenness of any area. So, the basic formula for NDVI is near infrared minus red upon near infrared plus red. So, I have written the formula like it is band 5 minus band 4 upon band 5 plus band 4 for only for Landsat-8 dataset. And for NDSI means if we are interested in normalized difference snow index or water index, then we will use NDSI formula green minus shortwave infrared by green plus shortwave infrared. So basically, uh, it is band 3 minus band 6 upon band 3 plus band 6. And if we are interested in water index, so there is a modified NDWI. NDWI means modified normalized difference water index. It has a general formula of green minus shortwave infrared by green plus shortwave infrared. So basically, these two formulae are similar, but they are provided by different authors. One in 1994, and another one is 2006 in 2006. So uh, if we want to check the moisture level in a vegetation, so we will use NDMI, normalized difference moisture index, and it has a simple formula of NIR minus SWIR1 plus NIR divided by NIR plus SWIR1. So near infrared minus shortwave infrared 1 by near infrared plus shortwave infrared 1. So it has a basic formula that I have already written in my sheet for quick reference. So NDMI means band 5 minus band 6 by band 5 plus band 6. Right. So this can be only used for Landsat-8 dataset for normalized difference moisture index. So now if we are interested uh, to if we are interested to if we are interested to observe the clay mineral ratio or ferrous mineral ratio, so in that case we will use a clay mineral ratio with shortwave infrared 1 upon shortwave infrared 2. So shortwave infrared 1 is basically band number 6 and shortwave infrared 2 is basically band number 7 for Landsat 8 dataset. And it will help you in identifying the clay minerals with with the radiation or you can say the absorption with around 2.0 to 2.3 micron in the spectrum. So if we are interested in ferrous mineral method for 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 all the iron bearing minerals, then we will use the NIR band, means near infrared band, and shortwave infrared band, and this is a basic band ratio index for ferrous mineral, SWIR upon NIR. So this is basically SWIR1. So if we are interested in iron oxide ratio, then we will use simply red band upon blue band, and uh, red band corresponds to band number red band corresponds to band number 4 and blue band corresponds to band number 2. So this is basically a ratio of band 4 by band 2. And if we want to see the built up area, or if we want to see the landscape of our Landsat data, then we will use a normalized difference built up index, which is NDBI, normalized difference built up index, and it has a basic formula of SWIR. Means it basically uses the shortwave infrared and near infrared. So this basically corresponds to band number 6 and band number 5. So band 6 minus band 5 upon band 6 plus band 5. So in this way we can generate lots of spectral band indices, and in this two or more bands are away, two or more bands are responsible to create a spectral band index. And the next that we performed was a band ratio for alteration mapping, and we are basically interested in lithium bearing minerals. So this is a research article that I have already mentioned, Fernandez ETAL 2019, and the guy proposed a simple band ratio index for identifying the lithium bearing minerals. Like if you want to see the spodumene that is present in the Landsat images, then you will use the Landsat-8 band with band ratio 3/5. If you have Landsat-5 data, then you will use band 2/4, and if you have Sentinel-2 data, then you will use band 3/8. So I have already showed you the ferrous mineral method and iron oxide mineral method and all the clay minerals method and their respective band ratio. And the next we can do is that we can perform the RGB band combination, means red, green and blue band combination for classifying the images with different. Let's say we have we are interested in natural color composite, then we will use band 4, band 3 and band 2 for Landsat-8 dataset. Band so these band will so these natural color composite band combination will generally help you in identifying the vegetation or the flora. So the interpretation that you can see is that healthy vegetation is green and unhealthy flora is brown. So and also urban features may appear as white or gray, and water can be dark blue or black. And let's say for color infrared band combination, we will use band 5, band 4 and band 3 in respective order, means band 5 first, then band 4, then band 3 for identifying the means chlorophyll basically reflects the near infrared light, and this band basically used to identify the vegetation of the area, and dark area are water and urban areas are white. So again we can use shortwave infrared 764 band combination, and then we will use band 7, band 6 and band 4, and they have their own interpretation. For agriculture we can use band combination 652, and they have their own interpretation. For healthy vegetation it appears dark green, and for bare earth area it appears magenta hue, and for simple geological feature that you can see like fold faults and the lithological contrast, then you will use shortwave infrared 2, means 7, band 6 and band 2. If you are interested in in observing the bathymetry of that area, then you will use band 4, band 3, and band 1. So this is a generalized table that is taken from ISRI ArcGIS blog, and they have generalized uh, uh, all this RGB combination, color composite combination 432764543, and they have their own application actually. So these are the maps that were imported from ArcMap in ArcGIS software, or you can see the ArcMap interface. So this is for NDVI, normalized difference vegetation index. This is for NDSI, normalized difference snow index, or modified normalized difference water index. This is for moisture index, and they have their legends. You can see the legends. You can see the brighter the uh, the the dark blue area with which has the high value of NDWI, means water index value. These are basically showing the water pattern, river pattern, you can also say. And if we are dealing with vegetation index, then the high value means the dark green portion are the healthy vegetation area, and the white portion has a low vegetation area. So these are basically the high and low value you can see in this exported map from ArcGIS 10.4.1. And we can further interpret for lithium mineral also. This is normalized difference built up index, and it has its own scale, or you can say it has its own legend. And based on the legend, we can classify the highest value and the lowest value. Lowest value of NDBI index is basically the sky blue color, and the dark values and the darker region are having the NDBI highest value, NDBI highest values. And for ferrous minerals, it has its own legend, and we can interpret, and we actually need your suggestions in this interpretation. We actually need your help in this interpretation process. This is iron oxide mineral. For iron oxide mineral, it has its own generated map, uh, and there are various color composite maps also. So I would like to show you the ArcMap interface. So this is the ArcMap interface, and let's say if we are interested, starting from the initial stage, these were the 11 bands actually, and we have converted this DN values to the reflectance, and let's say I'm showing you an example for band number 8. Now this is band number 8. So we basically use the arc toolbox, and it is nothing but a toolbox for all the ArcMap purpose we can use. So we are interested in raster data set, so we will use the arc toolbox, and under this arc toolbox we will use uh, the spatial analyst tools, and inside spatial analyst tool we will use map algebra, and this is raster calculator. So a simple formula will be used for raster, uh, for the atmospheric correction. So the formula for atmospheric correction is uh, yeah, this one. So if we want to convert the TN values to TOA reflectance, then we will use the band specific reflectance multiband. Multiband means for every band we will use the reflectance multiband, which is 2 raised to the power 2 into 10 to the power minus 5, and multiplying this with the DN values means for band number 8 we will use band 8, and reflectance add bands plus reflectance add band. Reflectance add band value is already mentioned in our metadata, which is nothing but minus 0.1, and then we try to perform the sun angle correction, which is the ratio of TOA reflectance that we have already calculated divided by sine of sun elevation. So sun elevation was around 0.39, and it is already present in our metadata, and the sine of 0.39 is 0.6391. So for this band we will use the raster calculator. This is our raster calculator. So this is 0.00002 multiplied by, this is reflectance band 8 multiband 8 into band 8, the raw DN value. This is band number 8. Okay, bracket close, multiplied I think we will use addition, but this is minus 0.1, so plus minus minus, and then close the bracket. So this is a DN value to TOA reflectance conversion, and by dividing this with the sine of sun angle, which was around sine of 0.39, which is basically 0.6391 that I have already calculated. So dividing this, and output raster file should have the name as band 8, band number 8. So it will take some time. You can see this, it will take some time to to correct the atmospheric effects which are generated from scattering and radiance. So I think I need to pause this video for a while. So the wait is over, and you can see band 8 which we have corrected for all the atmospheric effects like sun angle correction, and before sun angle correction we have converted the DN values to TOA reflectance value. This is band number 8, and we are interested in small portion of that area based on our topo sheet number 72L by 6, and based on the coordinates we have created a shapefile. This was the shapefile of that area, and we will clip this, area. Now wait a minute, it is taking time. So for clipping the area, this desired area, we will use again Arc toolbox, and we will use the data management tools, And under the data management tools, we will use Raster, and under Raster we will use Raster processing. We will come for Raster processing, and this is clip option for clipping the desired area. So input raster will be band number 8. So simply drag and drop here, band 8. This band 8 is corrected, atmospherically corrected band 8 data, and output extent will be the shape file, export output, correct. And we will use the name of the output raster dataset will be band 8 clip. All right, so take these options as it is and press OK. And again it will take some time to clip this portion, and this is actually the area of interest for topo sheet 72L/6, and it will take some time. So let's pause the video again. So a layer has been created with band 8 clip. This is the clipped portion, so let's uncheck this band 8, and this is the small portion that we are interested. Let's uncheck this export output also. This is shape file, and let's zoom to the layer. So this is the area of interest for band 8 only. Since band 8 is a panchromatic band with around 15 meter resolution based upon its wavelength, so similarly we will correct all the Landsat-8 bands, which are nothing but 11 bands, and similarly we will correct all the atmospheric effects, and then we will clip the desired portion based on the export, based on the shape file that we have created for the 72L/6 topo sheet number. And for clipping we will use the arc toolbox, and again we will use the raster processing, and under raster processing we will use clip option, correct, for clipping the sorry, for clipping the area of interest. So make sure that these bands, these shape file and your bands, the raw bands are geo referenced correctly. So uncheck this option, and in this way we can correct all the atmospheric effects. And after this we will use different techniques for spectral band indices, and I have already explained the how to generate the spectral band indices for vegetation, for the moisture, for the snow index, water index, or for the geological mineral index like clay mineral, ferrous minerals, or the means we are basically interested in lithium mineral. So for lithium minerals we will use the band ratio. Simply it was 4/7, and 4/7 for lepidolite, and 3/5 means band 3/band 5 for lithium pegmatites. And these band ratio relationship are for Landsat-8 data, and these are actually taken from a paper of from 2019, Fernandez ETL 2019 paper for the lithium mineral detection using the remote sensing technique, correct. So uh, I would like to use the NDVI technique also. So for generating the spectral band indices, we will use the some of the general indices like NDVI. So it will basically deal with the raster processing. So again we will use the raster calculator for the same purpose. So under the spatial analyst tools, there is an option raster calculator under map algebra, and you will simply double click this option, and the we will use the condition for float, because digital number values can be in float values, means in decimal, uh, means we can use the floating values. Means if we are subtracting the digital number 1 from digital number 2, then we will use a floating range value condition. That will be, so it will be for, if we are interested, let's take an example of NDVI. So if we are interested for NDVI, then we will use band numbers. For NDVI, we basically use near infrared minus red upon near infrared plus red. So for the same Landsat 8 data, we will use band 5 minus band 4 upon band 5 plus band 4. So band 5 means the corrected band 5 data, corrected band 5 data minus corrected band 5 data minus band 4 atmospherically corrected data, divided by again we will use the floating condition, band 5 plus band 4, means NIR minus red divided by NIR plus red, and name this output value, name this output raster as NDVI, and simply press OK. Error in output. Okay. So we will use another name like NDVI because it is already present. So I will use NDVI1, and then will simply press OK. So it will take some time to create the NDVI map, NDVI spectral band index map. So let's pause the video again. So again the wait is over, and we have created the NDVI layer. This is NDVI1. So we will use zoom to layer. This is NDVI1. Okay, but NDVI1 is for it's basically a vegetation index for showing the vegetation, for showing the healthy vegetation area. So we will change its color. So double click on this NDVI1 layer, let's say, and we will go for the symbology, and under symbology we will use we will go for classified, and we will classify it into 8 classes, correct? And we will use the color ramp, let's say in green color, from light one to darker one, and wait from light one to darker one, and simply press OK. Oh, sorry, again my mistake. So the the so the darker value, so the darker colored region, dark green colored region will have the high NDVI value, means high normalized difference vegetation index value, and the and the brighter areas are basically having the low NDVI value. So so we will take this in. We can use the layout view option for seeing this in for exporting this map. We will use the layout option and we will insert the scales and the legends for different maps. uh, for this map we will use the legend also with a scale. So the darker portion, so the darker portion is basically indicating the healthy vegetation area, and this is comparatively less darker, and it can be anything. It can be anything like it can be the landscape also, or uh, it can be a less vegetation, means uh, area, means it can be a built up area also, or it can be a agriculture area also. So actually it requires a good interpretation knowledge. So actually we basically need uh, a good interpretation from our professors and mentors. So in a similar way, we can use different indices like NDWI, means normalized difference, water index, and we can use clay mineral index also. Let me show you the lithium bearing minerals for this uh, as an example. So let's pause this video. So for lithium bearing pegmatites, or for spodumene also, it is proposed that we should use band 3 upon band 5 for Landsat-8 data. So again we will use the raster calculator for the same purpose. Arc toolbox, again raster calculator, and band 3 upon band 5 for spodumene. So band 3 is, we will basically use the corrected as well as the clipped area. Right now I am showing you the process how to generate the indices, or how to generate the band ratio. So band 3 divided by band 5, this is band number 5. Where it is, yeah, this one, this is band number 5. So band 3 upon band 5, let's name this output raster as spodumene, 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 and press OK. And again it will take some time to create the raster output layer here in the table of content. So let's again pause this video for a while. So the wait is over, and we have created the spodumene layer with which has band ratio of band 3 upon band 5. So this is let's uncheck this NDVI1 NDVI output layer. and check this spodumene, or you can say the lithium bearing mineral, pyroxene mineral group. So let's change its color ramp. So double click the spodumene and go to the symbology option, and use 8 classes first, 8 classes, and let's say color. So here I am using a funky color like this one, this one, and simply press OK button. And this is the layer, right? So let's clip this area because we are interested in this area only. So again go to the arc toolbox, and inside inside the data management tool, go to the raster. Under the raster you will see the option raster processing, and then clip this video, clip this clip this imagery, spodumene imagery that we have generated. So this is input raster spodumene, and this is the shape file, and simply spodumene clip will be the output raster dataset that we will generate here, and you can see this in table of contents. So just press OK as it is, leave it as it is, and close this arc toolbox, and again wait for some time. So let's pause this. So this is the clipped portion. So let's uncheck this spodumene layer and zoom to spodumene clip layer, correct, and okay, and then change its color, use a different color, like take this blue, or different color ramp you can select actually. So let's take this color ramp and classify it into 8 classes for this time, and color was let's take this color, and simply press OK. So this was the desired area, and you can see the darker green portion area has the high spodumene, you can say the high spodumene index, high spodumene band ratio index. So it is basically a band ratio of band 3 upon band 5 for Landsat-8 data. So a good interpretation is required for this kind of work. So we can see various patterns and various we can actually see the river pattern also, or we can actually see different landscape patterns also. So a good interpretation is required, and we basically need your help for this purpose. So we are basically trying to show you the process that we have utilized for the for the for for the generation of a spectral band indices, or you can say the RGB combination, or for the atmospheric corrections. So there were different methods that we have used till now, and we will also use some more method if it is related to our project. So uh, after creating the spectral band indices, we have used the band rationing technique for for let's example, we have used the band 3 upon band 5 for the spodumene mineral detection, and then we will use the RGB combination also. And the literature suggests that we can use the different RGB combination for different purpose. So if we want to if our purpose is to detect the lithium bearing minerals, then we will use specific RGB combination. So I would like to show you a paper which is related to RGB combination for lithium mineral detection. So this is a paper uh, which is which has different authors, mainly J. Fernandez, and it is published in year 2019. And they have worked for lithium detection and using the different data sets like Landsat-8, Landsat-5, Sentinel-2, and Raster data also. So the basic RGB combination, I would like to show you the RGB combination for detecting the lithium bearing minerals. They have proposed in their paper is was 492, 511, 4. These were some of the lithium bearing combination. Uh, but this is for Raster data. Sorry, this is for Raster data, and for Landsat-8 data, they have used 327, 3211, 7311. These were the they have proposed actually in their paper, and they have used bands 3 to 7, 3 to 11. There were different band combination for different mineral features detection. So if our purpose is for lithium bearing minerals, actually we have created all the composite band images, and I have already showed you I have already shown you in this progress research paper, and this was for NDVI, this was for different indices, and these were the composite band images. All right. So different composite bands for different mineral detection we have used. So I would like to show you an example for lithium bearing minerals for using the band 3, 2, and 7 combination. So we will use Arc toolbox, and under the Arc toolbox we will use data management tools, and under data management tools we will use, because we are dealing with the raster data set with different decimal number values, so we will use raster, and under raster we will use raster processing, and here you can see the composite band option. For composite band, RGB combination, composite band image. So for the same purpose, 3, 2, and 7 bands will be utilized for lithium bearing minerals. So input raster will be in according to band 3. First band 3 will come, and then band 2 will come, band number 2. Here is band number 2, and after band number 2 there will be an option for band number 7 also. So we have used band 3, band 2 and band 7 for lithium bearing minerals, and this band ratio combination was proposed by an author in his paper. So 3 to 7 will be in order, and output raster name will be composite band spodumene, spodumene, spodumene. Okay, and then simply press OK. It will take some time to create a RGB composite band image. So without wasting any time, let's pause this video for a while. So we have generated the RGB composite band image, and this is the RGB composite band image. So zoom it to the layer. So this is RGB composite band image with different bands. It's look amazing. If you zoom it to the layer, zoom into this layer, you can see various features, and we basically need your help in interpretation. These are showing some stream patterns, and based on the NDVI result, we have observed that these were the vegetation portion, and these were some of the landscape portion. And if we wish to clip this image, then we will basically we will clip this image for the specific area of interest. So we will clip this image again. Just drag and drop this input raster, composite band raster, and the shape file, and the output raster will be composite band spodumene clipped. OK, press OK and close this arc toolbox button, and again wait for some time to generate the clipped portion of the area. So alright, we have clipped the area. So uncheck this option, composite band spodumene, and this is composite band spodumene clip. Uncheck this shapefile also, and then zoom to layer again. So this is the RGB combination of band 3, band 2, band 7 of Landsat-8 data, and this is basically for lithium bearing mineral. This feature we can see for lithium bearing mineral, and if we want to export this map, then we will use the layout view option, and inside the layout, and this is the layout view option, and we should change this like spodumene composite band, composite band 3 to 7, because we have used band 3, band 2 and band 7 in order wise. So this will be the title of the exporting map. So simply click on the file option, and export map option is present here. So map will be exported and saved the path you wish to save your map. So write this composite COMPSITE composite 327 save. Correct. So it will take few seconds to save this exported map. Okay, so minimize this window and open the exported map path. So this is the path. ArcGIS data, Jamui was the area, and inside the output map, this was the composite 327, right? So this was, my bad, this was spodumene, SPOT. Please check this spelling, ignore this spelling and see the image, because I am just showing you the process or the ArcGIS interface. Under the ArcGIS interface, how we will create the composite band, how we will generate the spectral band indices, how we will correct the all atmospheric effects. So this is the exported map, and we and I have exported it in PDF form. We can also export it in .tif format also, or .jpg or .png format also. So this was the working, and we will use different composite band combination 431, 23, 257, and all the band combination have their own significance, and based on different band combination we will classify, we will detect the minerals that we are interested. And this is the unclipped portion, because this is indicating all the Landsat entire Landsat-8 data, and under this we have a small portion of 72L by 6, means 4 coordinates. Under this coordinate we will create a image of every indices. So we have achieved all these three processes in this video. We have created the spectral band indices. We know how to create the band ratio of different for different purpose, and we know how to create RGB composite band images. So this video was only to this video this the main purpose of this video was to make you aware about all the processes and the interface of ArcMap, and how we can generally use this technique for the mineral exploration or land cover classification, and later on we will use principal component analysis also for this purpose. So this was the main technique, and we will use it for every bands, and for every atmospheric correction is for every bands, and the RGB combination for every minerals in which we are interested, and we will clip the portion as per our area of interest. So this video was dealing with all this stuff, and we actually need your help in interpretation also. And thank you so much for all your attention. Have a good day.